Saxon Advanced Mathematics. Lesson 33, we're taking a break from the other kinds of problems we've been doing, specifically all that trig stuff, and we're going to do just a little straightforward geometry. Quadrilaterals are four-sided polygons. Right? There are three different types. The first one is the hardest kind for me to draw. There are no parallel sides. It's just a random hot mess, okay? Those we're not going to talk about very much. The second kind has one set of parallel sides, one pair of parallels, and that has the fancy name of trapezoid. Okay? We're going to come back up to those, and we're going to talk about those a little bit more at the end of the lesson. What we're going to talk about at the beginning part of the lesson is this, the third kind of four-sided polygon. I'm going to write this, three types. Okay, and here's the third kind. This has one pair of parallel sides, and here, let's give these the double arrow. So these guys match, and these guys match. Oh, I missed the line there, but you get it. This has two pairs of parallel sides. And this category is called a parallelogram. Fairly easy to remember that a parallelogram has got all the parallels going on. Trapezoid is just a weird freaking name. I don't even know what to say about that. We're going to talk about the parallelograms first, like I said, and then we'll come back and talk about this some more. So, parallelograms, two pairs of parallel sides, but the set of parallelograms can be divided. Draw that picture. Draw a nice big circle in here. This subset of parallelograms is the group of rectangles. And as you know, rectangles have two sets of parallel sides, right? And they also have, so let's draw the little lines on here, right? Those are those arrowhead thingies like we had here. These sides are parallel, these sides are parallel. But the other thing about rectangles that's cool is that they have right angles in the corners, right? Now, over here, draw another circle and have it overlap some. This category of parallelograms are called rhombuses. Right? And rhombuses they're like squished squares, where all four sides are the same length. There's no right angles, but they are parallel. I'll make this the double arrow side, right? These sides are parallel, and these sides are parallel. So both of them meet the description, right? Two pairs of parallel sides. These have right angles, but unequal lengths of sides. The sides are the same length, but there's no right angles. This interface in between them, the objects that are rectangles and rhombuses, this is where we meet our friend, the squares. And remember, a square has the equal sides of the rhombus and also the right angles of the rectangle. So a square is both a rectangle and a rhombus, and all of them are parallelograms. Lord have mercy, right? That's a lot of stuff layering in on top of each other. Now, if you want to learn about parallelograms, you should go to page 235. I'm going to write that there in great big letters. And I'm going to show you that on page 235, sorry about that big shadow, John has these boxes that tell us first about rectangles, then about rhombuses, and then about squares. It gives us specific details. Now here's the thing. I want you to read these lists, and I want you to look at those and go, okay, yeah, that makes a certain amount of sense. It's a lot of gobbledygook, but it makes a certain amount of sense. I don't want you to memorize this. I don't want you to spend a lot of time trying to cram it into your head or worrying about it, because we're not going to go very far with it. And it really, in the scheme of things, is not going to matter a lot in what you do, okay? So there are some examples that relate to this. It says, let me turn the page. I'll just show you how to logic these out so you can solve them, because I think they do pop up a bit in the homework, but not for very long. The diagonals of a certain parallelogram are of unequal length. Which of the following could it be? A rectangle. B, a square. Or C, a rhombus. Okay, we could look at those boxes that I just showed you on page 135, and we could read the fine print and figure it out. But you know, ugh, that's how I feel about it. Let's draw pictures and see if we can figure it out. What they're asking us is, these are the diagonals, right? Are these going to be the same length within this shape? So I drew a rectangle, I drew the diagonals, and I say these look pretty equal to me, right? They should be the same. How about a square? Well, that seems even more logical. They're going to be the same length, right? Now let's draw a rhombus, which is a box that we shoved over, right? So it's kind of like this. And I can see, just by using logic in the pictures, look, the diagonal, this one's going to be way longer than that one, right? The right angles keep everything square and the same, but these are unequal. So I'm going to say that C, rhombus, is the shape that gives me unequal diagonals, and that's the right answer, right? So again, you can look at the lists of properties, and it would have told you that, but it would have said things like, the diagonals form four congruent isosceles right triangles, and you would have had to decode what does that mean. Just draw the pictures and use logic and you'll be fine. 33.3. This is similar. The diagonals of certain parallelogram are not perpendiculars. Perpendicular. Diagonals not perpendicular. There. And the choices are A, rectangle, B, rhombus, C, square. Same as last time, but in a different order. Okay, so what they're saying is that these lines that go from kitty corners, do they meet at a right angle or not? So let's draw them. Do those diagonals look like they meet at a right angle? I would say no. I would say they are not perpendicular. Let's try a rhombus. That's the shoved over square, right? I know you did that when you were a little kid, because I did too, and it was the best. you played in cardboard boxes. And that was the only problem, is they would always tip like that, right? I always wanted to keep them perfectly square, and my brothers would thrash through them and knock them over, and it was terribly upsetting to my desires to have everything perfect and straight. But you know what? That's just how it was. Is it possible that these meet at right angles? I mean, it kind of looks like it. It's kind of hard to tell. It could be just because my drawing isn't accurate. So I'm going to go back to those squares of information. I'm going to look at rhombus and see what it says, because I think that the diagonals might be perpendicular, but I can't tell. Oh, and number 3 on page 235, in the rhombus section, rhombus section. Hi, Grace. Oh, she's coming to lick my arm. Hello, child. Hello. She's standing next to me expecting a little bit of petting, so you know, that's what has to happen. Good girl. I'm teaching math. Do you mind? Good girl. Did you hear her breathe a big slumbering sigh? Good girl. Okay, drop. All the way down. Good girl. Okay. In the rhombus section on page 235, number 3 says diagonals are perpendicular. So I'm going to write yes, perpendicular. My picture's a bit iffy. Now for the square, I'm going to try it again. Okay, those look really good. That looks very perpendicular. Again, I'm going to check for a square. It says all the properties of a rhombus apply. So that's number 2 on page 235, square section. And so that tells me that yes, it is perpendicular. My pictures didn't complete, this one looks better. This one doesn't look so good. This does not look like a right angle, but it looks close enough to me that I thought, well, maybe. So that's why I went and looked in the book. This one, I'm pretty sure it's not, and that's one we were supposed to find. So the answer is A, rectangle, and that's correct. Okay. 34, there's one more. I was trying to decide if I should flip the page or not. I think we'll be off. Okay. Given a parallelogram whose diagonals are congruent. Diagonals are congruent. Parallelogram means that it's got 4 sides. Each pair is equal. So it's either a rectangle, a rhombus, or a square. We know that a rectangle has equal diagonals. A square has equal, a rhombus has unequal. So this says, given a parallelogram whose diagonals, oh, I can't talk. Given a parallelogram whose diagonals are congruent. Okay, so that would be one of these two. Which of the following must be true? Okay, so here are my shapes. This is a parallelogram with congruent diagonals. This is also a parallelogram with congruent diagonals. The rhombus is not part of this club. I'm crossing him out. All right, so let's look at the conditions. All 4 sides have the same length. Well, it's true for this one, but it doesn't have to be true, right? So no, they don't have to be the same length. B, the diagonals are perpendicular bisectors of each other. Well, that's true for this. Does it cut this one in half? Maybe. Let's look at the next one. All 4 angles of the parallelogram are right angles. That sounds the most right to me. And that's correct. Again, I'm trying to use logic instead of those boxes on page 235, but I do have those boxes to help me sort it out. All right, that's all I want to say about parallelograms. And really, the most important thing I want you to take away from parallelograms is this. There are rectangles, rhombuses, and squares between them. And they're similar in that they all have two pairs of parallel sides, but there are some important and interesting differences between them. This picture matters to me that you understand. Okay, so that's all we said about parallelograms. Now let's talk about trapezoids a little bit, and these are more fun because we're going to do some calculations with them. Okay, so a trapezoid. Trapezoids are interesting. We usually put the parallel lines on the top and the bottom, and we call those the bases. Okay, these lines are not parallel. These lines are parallel. We usually call this base 1 or B1, and we call this, I'm pointing at this line, and we call this line base 2, or we abbreviate it like that. And then exactly halfway between the top base and the bottom base, we have what we call the median. And the median is equal to the average of B1 and B2. And we're going to expand on that in just a minute. All right, so it's a very orderly kind of arrangement. So, and there's some properties of trapezoids at the bottom of page 237 and again on page 238. They're in boxes. Whenever you see something in the book written in a box, you know, oh, that's probably kind of important, but we're not going to sweat it. All right, I'm not going to spend a lot of time going through those because they kind of are insanely double-speaky. I don't know. It just annoys me. And here's the thing. If it annoys me and I don't think it's important, you don't have to worry because very little in math annoys me, and I usually think it's all important. So this, you know, is definitely a side topic. All right, so John's giving us a parallelogram. It looks something like this. He's calling this B1. Oh, and he's putting these little lines on here to show us those sides are parallel. He's calling this B2. And he's measuring from top to bottom at a right angle. And he's telling us this is called H. Huh, sounds familiar, right? And he's asking us to derive a general formula for finding the area of this figure, this trapezoidal zoidy. So here's what we're going to do. We're going to divide it into two triangles. We're going to call this one, we'll call it A1 and this one A2. Okay, so what we're going to do is we're going to find the area of A1. Okay, it's a triangle, so base times height divided by 2, right? The base is this, right? We can kind of visually peel this corner and flip that triangle up, right? So it kind of looks like this. The base will be B1. The height of that triangle is H. Base times height divided by 2, right? The area of the second triangle equals B2 is the base times the height divided by 2. So to get the area of the whole trapezoid, zoined, I put it in an extra end. It'll be those two added together. And I'm gonna put the H in front because it just looks neater. H times B1 over 2 plus h times b2 over 2. And we can add those. hb1 plus hb2 all over 2. And then let's factor out the h. I'm going to scooch up a little bit so you can see better. I'm going to factor out the h from each term, and I'm going to factor out the 1/2. So the formula becomes 1/2 times h times the quantity b1 plus b2. Okay, so I'm just using algebra here to simplify. And this is the formula that we derive, okay? Now, anytime you want to find the area of a trapezoid, if you want, you can either memorize or derive this formula, or you can just remember, oh, this is super easy. You just find the area of this one, the area of this one, and you add them together, right? Normally we would have numbers, not just letters. So you don't have to fool around with the formula if you don't want to. All right, but it's easy enough to derive that formula too, if you'd like to. Okay, keep this in mind because I'm going to show it to you again in just a second. Ready? Example 33.6. Where is it? There it is. The figure shown is a trapezoid whose area is 175 centimeters. All right, let me draw for you. It looks like the way I used to draw shoes once upon a time. We're told this is x. We're told this is 2x plus 8. And we're told that this is 10. Okay, and we're also told that the area equals 175, yes. And that's in centimeters. So we'll add that in at the end. We're supposed to solve for x. All right, well, there's two ways we can do this. The first way is by using the formula. We just derived it. The area of a quadrilateral equals 1/2 times the height times the first base plus the second base quantity. All right, so we can plug this in, plug in the information we have. 175 is the overall area. That equals 1/2 times the height, which is 10, times the first base, x, plus the second base, 2x plus 8. Okay, so we just use the formula to plug in what we know. Now we'll simplify. Quickly I see, oh, let's do the 10 and the 2, and we'll get just a 5 instead. 175 equals 5 times, and then let's add these like terms. 3x plus 8, yeah? And then we'll distribute. 175 equals 15x plus 40. Subtract 40 from both sides. 135 equals 15x. And how many times do you suppose 15 goes into 135? Well, what my brain sees is this. If there were 15 more here, this would be 150, and then it would divide by 10. Because 150 divided by 10, right? Or 150 divided by 15 would be 10. So 135 divided by 15 must be equal to 9, right? Because I have to subtract 115 to get it to work. All right, so that's how I figure out that x equals 9. I used the formula and just plugged in the values. However, let's pretend I didn't have the formula right in front of me, because we just did that in the last problem. So it was handy and convenient, and I knew it was coming, so I knew to remember. But let's say that you're just tooling around and you suddenly get a problem like this, and you don't have that formula right in front of you, and you don't want to derive it because you're a sane person and you want to make it as easy as possible. Then what we do is we simply divide it into 2, call this A1 and this A2, and then we'll do the best we can to come up with areas for those and know that they should add together to be 175. So I want to do this on another piece of paper so I can keep it right in front of me here. All right, so what we're going to do is we're going to say A1 equals base x times height 10 divided by 2. And the area of the second triangle equals base 2x plus 8 times 10 divided by 2, right? And we know that A1 plus A2, those two triangles, has to equal 175. John gave us the answer. Okay, so now I'm going to substitute these two in here, but I'm going to simplify them first. Here, this is going to become 5x. That reduces to a 5, and then I'm going to distribute before I put them together. So this will equal 10x plus 40, right? 5 times 2 is 10, 5 times 8 is 40. All right, so now I'm ready to plug it in. So now I'll say 5x plus 10x plus 40 equals 175. All right, I'm going to add like terms, and I'm going to subtract the 40 from both sides. And I get 15x equals 135. And that's exactly what we got last time. I remember my whole story about how if I added 15 to this, it would be 150. Then x would equal 10, but it's 15 less, so x equals 9. So I get the same answer both ways. So what it really boils down to, oh, I forgot to write this. Our number 1 method was by using the formula. Our number 2 method, I'll write it over here, is just by using the triangles. Okay? The moral of the story for me is if you've got the formula handy, fine, go ahead and use it. But if not, just use the triangles. You can never go wrong with using the triangles. It's not really any more work. You just have to remember how to put them all together. All right, so that's 33.6. We have one more problem in this lesson. I hope you're agreeing that these problems where we actually have numbers and are calculating, they are a lot more agreeable than those silly word problems. In the figure shown below, EF is the median of trapezoid ABCD. All right, let's see what the heck John's talking about. He has drawn for us a trapezoid. It's got a median. I'll show you. He goes like this, A, B, C, D, and then he goes E, F. And he tells us that this is the median. Then he writes these things on each of the lines. And he wants us to solve for x. What we have to remember is that the median is equal to the average of the top and the bottom. So we'll just plug in all of these values to this and see if we can get a nice value for x, okay? So the median, 4x plus 1, equals the top, 2x plus 2, plus the bottom, 7x minus 2, and all of this divided by 2. All right. I want to get rid of this denominator. One way I could do it is to divide both sides, top and bottom. Well, it's the same thing. I'm thinking you could cross multiply, or you could multiply by the least common multiple, which is 2. Either way, you get the very same answer. So I'm going to multiply this by 2, and I'm going to multiply this by 2, right? I'm multiplying at an angle. It's not squared. This cancels this. This distributes. So I get 8x plus 2 equals, and now let's combine like terms as we go. 9x, and look, those disappear. Oh, that's fun, right? These two cancel each other out. So now, let's subtract the 8x. Oh, isn't this fun when this happens? When it goes down to just 1, we get x equals 2. That is the answer to our problem. Yay! Okay, so that's all we have to remember when we're trying to solve something that relates to the median and the basis of the triangle. Okay, these last couple problems that we've done where we actually are calculating and using geometry facts to set up algebra, these are good. I like these problems. The ones where we're talking about definitions and looking at those dumb boxes and trying to figure it out, those I don't care about. I know there's some in your homework and I want you to do them, but I don't want you to worry about them. Just do the best you can and move on with your life. All right, that's the end of lesson 33. Thank you, goodbye.